Okay. Let's take a look at what happens, the effect of the sample size. What happens to the sample size on the standard error of the mean? So let's take a look at different sample sizes. We have a distribution of 5 feet 9 American 5 foot 9 inch American males. Their mean weight is 160 pounds and their standard deviation is 10 pounds. So we have a population of men all the same height. This number 5'9" is not going to come into our calculations. It's just here to remind us that we're dealing with people that are all the same height. Their mean weight is 160, so the population mean is 160. The population standard deviation is 10. Find the mean and the standard error for the sampling distribution of means for samples of size 36, 100, 400, and 1600. And we did have an exercise like this last class. Let's just recap it and get better at calculating these things. If we have a mean of 160 and a standard deviation of 10, then no matter what the sample size is, the mean of the sampling distribution is always 160, always the mean of the population. Okay, so the sample size can range in value from 36, 100, 400, 1600, but the mean of our sampling distribution, which is basically the mean of all the sample means, is always the same as the mean of the population. The standard error changes. So we get these numbers. If we take a look at the calculator, we're going to take, for the very first one, we're going to take 10 divided by the square root of 36. So if we go to our calculator and we do 10 divided by the square root of 36, 1.666 repeating, which when rounded to 4 decimal places is 1.6667. So that's how we calculate the first one. The next one, we take sigma 10 divided by the square root of 100. That's so easy, we don't even need our calculator for it. 10 divided by the square root of 100 is 10 divided by 10, which is 1. So notice what happened. The sample size increased, the standard error decreased from 1.6667 to just 1, basically. Okay, for a sample size of 400, we're going to take 10 divided by the square root of 400. Now, some of you can do this in your head. If you can't, just do it in the calculator. 10 divided by the square root of 400. The square root of 400 is 20, so 10 divided by 20 is 0.5. Okay, so we have 0.5. So now our standard error went down even further, 0.5. Sample went up to 400, standard error went down to 0.5. Let's increase our sample size to 1600, which is 4 times the previous one. 1600, so we're going to take 10 divided by the square root of 1600. Oops, that's wrong. 10 divided by the square root of 1600. Okay. 0.25, so our standard error goes down even further. So we increase our sample size, we decrease our standard error. Now we saw, yes, from the last lecture, that when we decrease our standard error, it's simply a measure of basically how clustered sample means are or how dispersed sample means are. So when we decrease our standard error, smaller standard error means more consistency, more clustering about the center. Bigger standard error means that the sample means are dispersed further away from the center. So as we increase our sample size, we decrease the dispersion. We basically have increased clustering about the center. Our sample means are closer to the center of the distribution. So as the sample size increases, the standard error of the sampling distribution of means decreases. And when the sample size is large and the standard error is small, more of the data values are clustered about the mean. Okay, and here's a picture of what's going on here. When the sample size is 36, notice that the center is generally low as compared to what happens when n is 1600. The center of the distribution is raised. You've got more of the data values falling in the center of the distribution when n is 1600. Now remember, these data values that are on the horizontal axis are sample means. So when we have a small sample, our sample means are more dispersed away from the center, and as we increase our sample size, we have sample means that are clustered closer to the center, so that clustering has the effect of raising the bell, basically the peak of the bell curve, so that it's higher, indicating that you have more sample means within that small space around the center of the distribution. So you have greater confidence that a data value chosen at random is closest to the true mean if you choose from the sample of the largest size, which is 1600. The range is smaller and therefore there is less variability in the data. So the sample means are closer to the population mean. And when I say the range is smaller, this is how we calculate the range. The center for each of these distributions is 160. But the standard error is different. If you subtract about 2.58 standard errors, it takes you to 155.69. And if you add 2.58 standard errors, it takes you to 164.31. If you subtract 2.58 standard errors in this case, when n is 1600, you have a low sample mean of 159.35, but when you add 2.5 standard errors, you have a high sample mean of 160.65. So the range between low and high is 1.29 here, where the range between low and high is 8.62 here. The lower, or rather the smaller range, means that you have more data values in a smaller range of space, more sample means in a smaller range of space, and that increase of sample means closer to the population mean indicates that you have better confidence in picking a sample mean that's more representative of the real population mean. So ideally, you want your sample to be as big as possible, because when you reduce your standard error, you increase the confidence that you're going to pick a sample mean that is reasonably close to the population mean.